Welcome back to this advanced manufacturing and process modeling course. So, we were discussing about the forming module, and we have already discussed about the deformation mechanisms, and which is basically caused due to dislocation motion. We have also discussed about the screw and edge dislocation. So, today we will start with the analytical solution of the deformation conditions while considering mechanics of metalworking by slab method. So, so the slab method is a common approach used in the mechanics of metalworking to analyze stresses and forces in processes such as rolling, extrusion and forging. So, it involves dividing the deforming body into thin slabs and analyzing equilibrium, stress distributions and flow conditions. So, plane strain conditions are applicable in this particular domain that is shown over here. So, why we are assuming plane strain conditions here? Because it is assumed that there is only the deformation is happening only in 2 dimensions and no strain in the third direction. So, it is assumed that there is no strain in the width direction. So, if we consider this is the width direction, so that is y, and so this is x. So, x y z. So, this is z. So, along the direction of the movement, so that is the x direction. So, so there is deformation happening in the x, along the direction of the direction at which it is pressed within the die. So, these are the die enclosure through which the ingot is pressed. So, this is the ingot material or ingot sample, and that is pressed, and this is basically the deformed object. So, the deformed, you can say this is as deformed plate that is coming out. So, there is deformation in the x direction, in the z direction, and there is no deformation in the width direction. Okay. So, so the material also, it is assumed that it is perfectly plastic. So, yield stress is constant and no strain hardening is happening. So, it is neglected, and friction at the interface between the slab and tools, that is die or rolls, follows Coulomb's friction of law. So, these are the basic assumptions that has been considered in this slab analysis. So, due to the change in longitudinal stress with x increasing positively to the left, so that you can understand. So, this is basically so x is increasing positively towards the left. So then so it is so the sigma x plus d sigma x into h plus dh. So, h is the height at any given point. So, that is shown over here. So, this is the height at the that bite location in the die enclosure. So, that this is the distance h that is shown over here. So, marked as h. So, and this is the initial height of the workpiece or the plate or the slab ingot. So, that is defined here as hb. Okay. So, or it is defined here as h0, that is the initial height of the specimen. So, so due to the so this is the h and the notation of h is clear. So, the now due to the die pressure at the two interfaces, so the resultant stress is basically 2 p w by cos alpha sin alpha into dx. Okay. So, it is basically, you can understand it from this diagram. So, it is basically this component that is dx by cos alpha, and this is the pressure applied. So, here basically we are taking this is the so dx by cos alpha, and it is the 2 p sin alpha. So, so why this is 2 p sin alpha? Because the pressure, it is acting from both the directions, that is from the top and also from the bottom. So, that is why it is 2 p, and then we are basically taking the horizontal component, because we are making a balance along the x direction. So, along the x direction. So, hence it is 2 p sin alpha. So, 2 p sin alpha into dx by cos alpha into w. W is the width of the plate. So, then so due to the die pressure at the two interfaces. So, taking the equilibrium of forces in the x direction and neglecting the product d sigma x dh. So, what we will get? So, if we make a product, so then sigma x into h plus d sigma x into h plus sigma x into dh plus d sigma x into dh. Okay, this is multiplied by w. Okay. So, then here if we so we can see the d sigma x dh. So, we can basically neglect that. So, it goes it cancels out here. Okay. So, then the equation gets reduced to sigma x h plus so h d sigma x, okay, plus because here there is minus sigma x w. So, that means so we have cancelled it. So, then sigma x so sigma x h and then sigma x dh, and so it is multiplied by w. So, all the terms are multiplied by w in minus sigma x h w. So, that means that this term cancels out, and then what is remaining, h d sigma x plus sigma x dh. Okay. And then here because we are basically taking the equilibrium forces along the x direction. So, then we need to add this term over here. So, then it is 2p tan alpha, that is what. So, sin alpha by cos alpha, it is tan alpha into dx, and then it is the whole expression is multiplied by the width w. So, then width so w not equal to 0, hence we can equate this term to 0. That is what is done over here. So, from the geometry, h may be expressed in terms of x as h is equal to 2x tan alpha. So, you can see it from this free body diagram that is shown over here. So, from here we can express h is equal to 2x tan alpha, that means 2h dh is equal to 2 dx tan alpha. So, if we put this expression of this over here, so then the above equation simplifies to so it is 2p tan alpha dx. So, we know that dh is equal to 2 dx tan alpha, that means it becomes sigma x dh. So, from here we are getting here plus h d sigma x plus p dh is equal to 0. So, to find a relationship between sigma x and p, sigma x is the stress along the x direction and p is the applied pressure. So, the equilibrium of forces in the y direction, that means in the vertical direction, that means in the thickness direction of the slab, which is expressed here as y, but it can also be expressed in the z, like initially we have mentioned that the width direction as y and the thickness direction as z. So, it is just the nomenclature. So, it can be very well written as z as well. So, we can we can do it here. So, then we are getting what we are getting. So, and in the y direction we get sigma z dx into w plus p, so cos alpha gets cancels out. So, p w dx is equal to 0. So, so as we know that so here we can see that so w dx. So, if we take the w dx as common, then we can get sigma z plus p is equal to 0. That means z is the sigma z is the stress in the thickness direction, that is the z direction. So, again, like because width cannot be 0, so w not equal to 0. So, then we can write sigma z plus p is equal to 0. That means sigma z is equal to minus p. That means it is the stress in the z direction, in the thickness direction is equal to minus p, which is compressive in nature. That is what is evident also, because the die is pressing, it is applying compressive stress over the deformable workpiece material. So, then we are arriving at this. So, since up to this point we have considered p to be a positive quantity. So, sigma y or like we have expressed here as sigma z. So, that means it is nothing but the stress in the thickness direction. So, sigma z is the stress in the thickness direction, stress in the stress in the thickness direction of the slab. Okay. So, hence, so it is compressive in nature, as evident from the minus sign of the P. So, we now relate the two principal stresses. What are the two principal stresses? So, we have discussed. So, sigma x and sigma z, and we have assumed plane strain condition. So, hence, so in this case, I mean two principal stresses we are now relating by means of yield criterion. So, for plane strain condition, the von Mises and Tresca criteria are equivalent, and what is that plane strain condition? It is like principal stress 1 sigma 1 minus sigma 3 is equal to 2k, that is 2 sigma 0. Sigma 0 is the yield stress of the material by root 3. So, which is can be defined as sigma 0 prime. So, here what is sigma 1? So, here sigma 1 is sigma x and sigma 3 is nothing but sigma z. Okay. So, then I mean, so as we have evaluated earlier that sigma z is equal to minus p. So, then what we can get from right from here? So, sigma x, so I mean so the plus p is equal to sigma 0 prime. So, that means we can evaluate the applied pressure P from here, which is sigma 0 prime minus sigma x. Okay. So, so substituting that into equation 1. So, this equation we can arrive at this expression, that is sigma. So, P is equal to sigma 0 prime I mean sigma 0 prime minus sigma x. So, here from here we can get. So, if we just write this expression again, so I mean that is sigma x dh, sigma x dh and plus h d sigma x plus h d sigma x and plus p dh is equal to 0. Okay, is equal to 0. So, now we have evaluated that P is equal to sigma 0 prime minus sigma x. So, then sigma x dh plus h d sigma x, then it becomes sigma 0 prime into dh, sigma 0 prime into dh minus sigma x into dh is equal to 0. Okay. So, we have sigma x dh here. So, it gets cancelled and h d sigma x plus sigma 0 prime dh. Okay. So, this is and it becomes equal to 0. So, then from here we can write h d sigma x plus sigma 0 prime dh is equal to 0. So, that means we can write as from here we can write that d sigma x by I mean sigma 0 prime is equal to minus dh, we are taking it in the I mean right hand side by h. Okay. So, this is the resultant expression, and then I mean if we integrate it. So, if we integrate it both the sides, then we can write from here as this is the resultant expression, sigma x by sigma 0 is equal to minus ln h plus c constant. Okay. So, the boundary condition is that at the entry to the die x is equal to b, h is equal to h b. So, please again we are going back to this I mean free body diagram. So, you can see. So, h is equal to h b at x is equal to b. So, then the axial stress equals 0. Therefore, constant becomes equal to. So, the axial stress, if we put the value of axial stress sigma x over here as 0. So, then we can get that ln h constant is equal to ln h b. Okay. So, then we have seen here that sigma x is equal to sigma 0, sigma x by sigma 0 is equal to minus ln h plus c. And we are talking about the limiting conditions when x is equal to b, h is equal to h b and the axial stress becomes equal to 0. So, I mean in that case we can get, so 0 divided by sigma 0 which is equal to 0. So, that means ln h is equal to I mean constant. Okay. So, then putting this value again over here, we get sigma x a by sigma 0 I mean sigma 0 prime, it should be sigma 0 prime is equal to we can see that ln h I mean, so it is basically h b. So, then ln h b minus ln h. Okay. So, then what can be written as sigma x a by sigma 0 prime is equal to ln hb by h. Okay. And so that means sigma x a is equal to sigma 0 prime ln hb by h. So, sigma 0 prime we know the from the distortion energy criterion 2 by root 3 into sigma 0, that is the yield stress ln hb by h. So, this is the the axial stress at the die exit needed to cause deformation under this ideal frictionless condition as sigma x a. So, this is what is shown. So, sigma x a is equal to 2 by root 3 sigma 0 ln hb by h a. Why h a? Because it is when it is the the final and initial height. So, so for example, if we just now equate it, so initial height say h a into initial area, that is a is equal to final height h b into the final area, that is a b. So, then we if we need to calculate, so that is the h b by h a. So, then it becomes a by a b, because why we are writing this expression, because the volume remains constant. So, volume is equal to constant in the deformation process. Okay. So, that is why we can write from here that h b by h a is equal to a a by a b. So, now we know that from this expression we know that we have discussed in the earlier class that the ratio between the initial area and the final area. So, that governs the reduction ratio, that is R. So, then what is R? So, R is basically nothing but the initial area. So, here initial area is say a minus the final area a b by the initial area. So, that means 1 minus a b by a a. Okay. So, that means so a b by a a. So, a b by a a is equal to 1 minus r. Okay. So, here we are getting that h b by h a is equal to a by a b. So, if we just, so from here we can calculate a by a b as 1 by 1 minus r. So, then if we are putting this value, so this is, that means it becomes h b by h a is equal to 1 by 1 minus r. So, then if we put this expression for this sigma x a, so then the expression of sigma x a becomes is equal to 2 by root 3 sigma 0 into ln h b by h a, that means ln 1 by 1 minus r. So, this is the resultant expression for the ideal frictionless condition, that is the axial stress at the die exit. Okay. So, so hope it is been understood. So, then we are moving into the uniform deformation energy method, that is another technique. So, it is an analytical approach used in metalworking to estimate the energy required for deformation. So, it assumes that deformation occurs uniformly throughout the workpiece and considers both internal and frictional contributions to the total energy. So, the assumptions are deformation occurs uniformly across the workpiece and material flow follows the principles of plastic deformation. So, the friction between the workpiece and tools is constant and follows Coulomb's law, and the material is isotropic and homogeneous. So, what is the derivation? So, the internal energy due to deformation. So, the internal energy per unit volume required to deform the material is given by plastic work, which is equal to 0 to epsilon f sigma d epsilon. For a perfectly plastic material, constant stress sigma is equal to k and u is equal to k into epsilon f. So, k is the shear yield stress and epsilon f is the final strain. Okay. So, the frictional energy arises due to the interaction at the tool workpiece interface. So, so this is the case that what we have shown over here. So, this is a typical tool workpiece interface. So, this is the interface. Okay. So, these are the tool workpiece interface, and so then Yeah, so assuming Coulomb's friction law, the energy per unit area is EF is equal to integration tau into V into dt is equal to mu sigma into V dt. Simplifying for uniform velocity V and constant friction coefficient mu, we can get that EF is equal to mu sigma into L, okay, where L is the length of the contact interface. Okay. So, I mean, so then the total energy, what is the total energy? The total energy required for deformation is the sum of the internal energy that we have discussed earlier. So, this is the internal energy term and this is the frictional energy term that we have evaluated over here, that is EF. So, it is has to be multiplied by the area, contact area. So, then the total energy becomes equivalent to, I mean, V, so internal energy multiplied by volume of the workpiece and I mean frictional energy multiplied by the contact area. Okay. So, EF into A. So, this is the total energy. So, for specific geometries, that is plane strain or axisymmetric conditions, the energy expressions can be further simplified to obtain estimates of forces or pressures required for metalworking processes. Okay. So, now we will move to the forging. We have already discussed how we can analytically calculate the stress strain conditions during, I mean, metalworking. So, we have discussed the mechanics of metalworking by slab method and also uniform deformation energy method. So, now we will discuss about the forging process. So, what is forging? So, forging is a deformation process in which the work is compressed between two dies, either impact or gradual pressure is applied to form the part. It is the oldest of the metal forming operations and dates back to perhaps 5000 BC. Today, forging is an important industrial process used to make a variety of high strength components for automotive, aerospace and other applications. So, these components include engine crankshafts and connecting rods, gears, aircraft structural components and jet engine turbine parts, etc. So, in addition, steel and other basic metals industries use forging to establish the basic form of large components that are subsequently machined to final shape and dimensions. Okay. So, the types of forging processes. So, forging is carried out in different ways based on working temperature. It can be classified as cold forging, warm forging and hot forging. So, what is cold forging, by the way? When we are doing the forging, which is when the temperature is above room temperature, but it is well below the recrystallization temperature of that particular material, and hot forging when we are processing the material beyond its, I mean, so hot forging temperature is greater than the, I mean 0.5 Tm, which is roughly the recrystallization temperature for a given material, and cold forging, it is temperature is way much lesser than the recrystallization temperature, that is 0.5 Tm, and warm forging, it is the temperature is somewhere in between cold forging and hot forging. Okay. So, it is of course, it is below the, I mean, recrystallization temperature, however, it is well above the room temperature and it clubs the benefit achieved by both cold forging and hot forging. We will learn about the merits and demerits of individual cold forging and hot forging processes in the, I mean, coming slides. So, and then, so this is the classification based on working temperature, and then the classification is based on source of power. So, based on source of power, the classification is forging hammer, applied impact load, forging press, applied gradual pressure. So, these are the based on the source of power and the application of load, the forging process can be classified broadly into these two categories. And number 3, based on the degree to which the flow of the work metal. So, I mean, then we can be forging can be classified as open die forging, flashless forging and also impression die forging. Okay. So, these are the 3 schematics which depicts about the open die forging. So, this is a typical example of open die forging, which is also resembles a typical compression test, and then this is the B, that is a case of impression die forging. So, you can see that the die is already having a impression of the final object that is going to be made. However, there is flash generated. So, in that way it is different. So, these are basically, so this segment, so So this is basically the actual component that is getting, I mean, for which the impression die is being used, and that impression is obtained in the component developed. So these are the flash regions. So these two regions are termed as flash. Okay. So these are the flashes that is generated, and then the third variant is flashless forging. So it is quite similar to impression forging, because here also there is a impression in the die that is getting, we are achieving in the forged part. However, in this case there is no flash generated, so that is why we call it as flashless forging. So it is the third variant. Okay. So moving on, so if we discuss the open die forging, so in this case the work is compressed between two flat or almost flat dies, thus allowing the metal to flow without constraint in a lateral direction relative to the die surfaces. The simplest case of open die forging involves compression of a work part of cylindrical cross section between two flat dies, which is the example shown over here. So this forging operation, known as offsetting or offset forging, reduces the height of the work and increases its diameter. So that is what you can see over here. So this is from the starting preform, we are arriving at a much lesser height. That means this is the H final and this is the H initial, and whereas so the H final is much lesser than H initial. So HF is much lesser than H initial, whereas the D final, the diameter final, is much greater than the diameter initial. Okay. So this is the basic concept in case that is shown over here in case of offset forging. Okay. So the analysis of open die forging. So if open die forging is carried out under ideal conditions of no friction between work and die surfaces, and then homogeneous deformation occurs and the radial flow of the material is uniform throughout its height. So as shown in this figure. So that is what is shown. So here it is the depict. So here the symbols depicts where that means small v is the velocity and applied force is designated as F. Okay. So this is what a typical case of open die forging. So now we move to the impression die forging. And so in case of impression die forging, the basic concept we have already discussed, that we are basically getting the impression that is kept over the die cavity. So this is basically the impression present already in the die, in the die that is used, and then it is basically the compressive load is applied, and then it is getting continuously pressed, and this is the intermediate stage, and after undergoing this intermediate stage, this is the final stage of the part, and these are the flash regions that is generated. So why the flash is generally provided here? So basically it is, as we know, that typically we do these forgings and in hot forging condition. So there are some scales and oxide surfaces that is generated over the workpiece which is undergoing the forging process. So the benefit of giving this flash region is that so the extra metal that is not needed to form the the workpiece as the impression is given in the die cavity. So that extra metal, so the oxide scales and all the dirt inclusion, so these are basically getting trapped in the flash region, and hence the generated component comes out to be clean and comes out to be free from these oxide skin defects and inclusions as well. So free from oxide skin entrapment and inclusion based defects, oxide skin entrapment and inclusion defects in most of the cases. So this is the benefit of keeping the flash region in the workpiece that is getting forged. So, the raw workpiece is shown here as a cylindrical part like that used in the previous open die operation. So, as the die closes to its final position, flash is formed by metal flow beyond the die cavity and into the small gap between the die plates. Forces in this process are significantly greater and more difficult to analyze than in case of open die forging. Okay. So I mean, so one thing need to be added here. So I mean, so the force versus displacement curve, if I draw, so this is a typical force and this is say typical displacement. So up to if I draw it, so if I just change the axis, so if I put it as the force generated, or or if I keep it as the same. So initially initially with the increasing displacement the force increases, and then after a certain displacement is reached, then with small increment the force increases significantly. Why this happens? This happens because of this flash generation. So when the flash is generated, so after that if the compression load is increases even further, but so it causes higher force application to the body undergoing deformation. However, there is no further deformation actually happens in the body, and so that is why after a certain peak load that we can come to know that the forging process is over, and the part is already forged or fabricated. So impression die forging, these are the typical KF forging shape factor values for various part shapes in impression die, and flashless forging is given over here. So in case of impression die forging, these are the KF values for simple shapes with flash, complex shapes with flash, and very complex shapes with flash. And in case of flashless forging, for example coining, the values are say like 6.0 and 8.0. So followed by that, if we go to the flashless forging, so please focus here that in this case we are getting exactly the dimension of the end part needed. So we are not there is no room for generation of any flash. So in case of flashless forging, the impression die forging is sometimes called closed die forging in industry terminology. However, there is a technical distinction between impression die forging and true closed die forging. The distinction is that in closed die forging, the raw workpiece is completely contained within the die cavity during compression and no flash is formed. So that is what is shown over here, and the term flashless forging is appropriate to identify this process. So the flashless forging imposes requirements on process control that are more demanding than impression die forging, because we do not allow flash formation in this case. And hence so most important is that the work volume must equal the space in the die cavity within a very close tolerance. Okay, so it is the best to part geometries that are usually simple and symmetrical, and to work material such as aluminum and magnesium, that is the non-ferrous and light alloys and their alloys. So the flashless forging is often classified as a precision forging process. So because of the dimensional tolerance that we can get, so that means there is no flash is involved, there is no need for any finish machining to arrive at the final dimension. So this is a precision forging process that is precision forged parts that can be manufactured by flashless forging technique. So so with this we are stopping for this class, and we will start in the next class. So we will analyze the forging process in plane strain. So thank you for today.